Thank you. So, when I put this presentation together, I had a couple of objectives. The first objective was to come up with the longest title possible. And I think you'll probably agree, achieving low latency security in today's competitive, regulatory, and high-speed transaction environment is indeed the longest title that you'll see today. So I think I've achieved that first objective. So my name's Darren Turnbull, VP Strategic Solutions. Now, what does that mean? It's a kind of a vague title, but essentially I'm part of the product management team within Fortinet, looking across a number of the different products that we have out there. So, it's about latency, so this should be a quick presentation. There are three main sections, so we're just going to go through and get some common agreement of what latency is, what time is, what we can do about that, and then apply that to a firewall architecture, and then look at some requirements we've seen from our customers that have driven us to produce the product sets that we have. So what is latency? I guess everybody has an idea what it is, but essentially, to us, it's about the reaction time. That's the latency, that's the delay. So you have to achieve something in a certain time, and there is a delay associated with you completing whatever task that is from when you've been asked. So in a financial transaction environment, obviously trading events take place all the time, and there is a delay associated with that event. Now, some of that delay is programmed into the systems, but some of the delay is not. But simplistically, you get that input, you make a decision, but it all takes time. And there are a lot of components within any system that are going to add to that latency, the application itself, the middleware operating system, etc., and the network components. And every part of that solution will add to the latency. It accumulates a little millisecond here, a microsecond there, and this all accumulates to give you the latency for the actual system. So what's the impact of latency? Why do we care? Why am I here? So if you look at different applications, some are more sensitive to latency than others. Now, media streaming, if you're watching a video, there'll be a certain amount of buffering takes place. So the actual latency, unless it's very long and it exhausts the size of that buffer, latency isn't a specific issue for you there. Voice over IP, if any of you have been involved in designing voice over IP networks, you'll know that there is a crucial latency budget because you've got people on either end of a call, and they'll only put up with a certain amount of delay before the actual call stops to be successful. Email, I mean, the speed at which people expect you to respond to email is one thing, but the actual latency of receiving email is not so much of an issue. Web browsing, and we've all sat there clicking on websites, and we want to get page refreshes very quickly. 2 or 3 seconds, I think, is the longest people will wait for a web page these days. Peer-to-peer networks, again, no real issue as far as latency is concerned. But in the financial space, latency is very important. And for financial markets, that time does equal money, quite literally, because you're looking to get an advantage over other traders that exist within the market. And you can only get that competitive advantage by being first to the market. And customers that we speak to about our solutions, they will measure the return on investment in milliseconds. They don't measure that return on investment in days, weeks, months, years. It's milliseconds. It's very surprising. So, you need to get competitive advantage. So you need to do the right thing, obviously. And the right thing, whether you actually act a transaction or you don't, someone has to, or something has to decide what the right thing is. But you have to do it first. You can't make time. You can't give yourself more time. But you need to use less of the time that's available. So what is the available time? Remember, we're looking at latency across the entire system. And the available time is actually the time that your competition will be using. That is the available time. You need to be quicker than them. So there is no magic number. You can't say for a financial transaction that the latency budget, if you will, is 200 milliseconds. Because if you come in at 190 milliseconds, you're first all the time. If you come in at 100 milliseconds, you'll beat everybody. So the available time is dictated by other people in the market. And that number isn't going up, it's coming down. So you have to get quicker. So why do we care about that within the firewall environment? Well, let's take a little look. So when you talk to financial customers, they are very paranoid about latency within their networks. It's not for no reason that the trading offices all congregate together. And this is because of, amongst other things, the actual latency across a wide area network. But with firewalls, typically firewalls were not designed for low latency. They're designed for security. And they are sensitive to packet size, connection rates, etc. And as we know, in this environment, latency is a bad thing. Therefore, firewalls, when we're just looking at latency, are also a bad thing. And the other bad thing about firewalls in this environment is, over time, they get more and more complex. No one removes firewall rules. Rules get added all the time. No one takes them away. And obviously, as that accumulates, you're getting thousands and thousands of rules. That's going to be very complex as a system. The other limitation you get with traditional firewalls is they don't process multicast traffic effectively. And by effectively, I mean quickly, for the purposes of this discussion. And a traditional firewall will drop multicast packets very quickly. There's not a lot of throughput you need to get to before you start losing packets. Because multicast has a particular challenge in that you get one packet in, you send more than one packet out. And firewalls typically are not designed to do that. So when you're looking at finance networks, there's a lot of optimization takes place within the application. That's where the smart stuff is. There's a lot of work goes into getting high-performance computing systems, etc. But the firewall is the last piece of that strategy because it's the complex piece. It's the piece that nobody likes. So why have a firewall at all? It's an interesting question that the finance houses will ask. Well, we don't need a firewall. Why do we need a firewall in this environment? Well, you obviously need to define what I say here, a trusted set. Who can talk to who about what? And the firewall is designed to do that. But you may also have a requirement to log what is going on, to monitor the traffic that's flowing between these entities. But also you may have to hide the topology of your network. Either you have to do that because you don't want to expose the internal workings of the network, or you have to resolve any conflict between duplicate IP addresses. I've had a lot of fun in this room today with duplicate IP addresses in this network, so I think we see the value of that, right? And also, there can be compliance requirements. You have to have a secure environment. So there is a need for a firewall. So having defined the fact that there's a need, and there will be a firewall between the client in this case, you see the router, a firewall, wide area network, etc., and the actual market or exchange floor. There is security requirements between those 2 points. So then we're looking at other issues around latency. And some things we can't change. So the serialization delays. This is the actual clocking in of, if you like, the bits on the wire. You can only have one bit on one wire at one time. Now, they're very quick, but it's still finite limit. We also have propagation delays. So propagation delays caused by distance. The speed of light is going to limit what you can do about that. And you can't fix the speed of light with a bug report. It is what it is. That is fixed. And the numbers you see on the sign there, they're the milliseconds to get to different destinations, actually from London. So we can probably add a few milliseconds to jump here. But those numbers make certain assumptions. They assume you've gone in a straight line. You know, so if it's 1,000 miles between here and London, you don't go in a straight line. The route that you take is dictated by the network that sits between here and London. And that network, you know, whether it's air, road, rail, etc., dictates where you go. Those numbers also assume that the data is traveling in a vacuum at the speed of light, doesn't stop along the way, doesn't get buffered, doesn't get any of this serialization delay, and it doesn't want to come back. So this is a one-way direction. So when you start looking at the latency numbers here, you really need to take that raw number and multiply it by 3, at least, to give you some indication of what the actual latency will be. So things that we can change. Features. Now, the more features you turn on, the less performance you get. You don't get something for nothing. Laws of physics still apply, even if you really, really don't want them to. The more you're asking a system to do, the longer it will take to do it. So you need to streamline the solution. But further, if you're looking at software solutions that give you that feature set, you are going to be limited by whatever general purpose CPU is applied in that solution. You can push off some features into hardware, but having solutions running in hardware is much more difficult than it is to implement something in software. Difficult in terms of doing the development, difficult in terms of making any changes, and extremely difficult in terms of reacting to any bug fix requirements. Fixing hardware is not straightforward. So you need a flexible approach. You need to be able to do what you can in hardware and implement certain features in software and ensure that you have the right thing running in the right place. And right, again, for the purposes of this discussion, is the place that gives you the lowest latency. So then you look at firewall architectures, and you get a lot of distributed solutions, different blades, different modules, different connectors, etc. And these architectures exist to solve problems. Nobody sits there and says, well, wouldn't it be good if we had multiple different cards doing different processing at different times? They're not doing that because they want to. They do that because they have to. But when you're generating these distributed systems, the actual latency isn't always the top of your mind. You've got other things to consider. There's a raw throughput, there's handling the actual session setup rates, etc. These are all things that a firewall needs to worry about. But latency isn't always the issue. And of course, with a distributed system, as you try and scale it, it gets more complex. How many management cards do you need? How many interface modules? How do I map from this interface to that interface? What are the trade-offs? Where are the bottlenecks? How does the system profile? What's going to break? This makes a distributed architecture much more complex. So then we look at multicast and unicast traffic. So I mentioned earlier about multicast. So multicast traffic is coming from a source. In the case of finance market, this could be market data information. So an exchange will be sending out the market data. Let's say a share price gets sent out. Send that out to all of their customers who subscribe to that service, and they pay real money for that data feed. And that data feed better be quick, and it better not break. Because they have to receive that information, make a decision on what to do with that information, and then act a trade. And obviously the latency involved is also considered when you get that market data. Now, having a firewall in the way, if you like, can be a problem. Because as I mentioned, firewalls typically don't handle that multicast data very efficiently. But the FortiGate product, there's some information over on the booth there, can provide acceleration for both unicast and multicast traffic. So let's look at the market data. As I mentioned, provided via multicast, because you're sending it out from one source, or probably multiple sources in terms of redundancy, because you're charging real money for this. There'll be a NAT, network address translation requirement, this topology hiding, or linking together disparate networks, etc. So you have to have something that can act and make that address translation happen. And that can be the source address, the actual multicast feed, or it can be the destination where it's going to within the trader's network. But if you look at the throughputs there, a traditional firewall can achieve 100 meg of market data throughput, which is a decent number. It's a big number. But if you want to get more than that with a traditional firewall, typically what we see is that the market data bypasses the firewall, which gives you limits, obviously, on doing that network address translation. And it also doesn't look good from a security audit perspective. What is that wire that's going the other side of the firewall? Oh yeah, that's the market data. We can't secure that. Not a good story to tell an auditor, believe me. So the Fortinet solution, if you get the right box with the right hardware to solve the right problem, can give you 4.5 gigs worth of multicast throughput. So comparing that to 100 meg is quite significant. And we don't know anybody that can come close to that, based on how we've engineered our solution. And how we've engineered it is we use this thing called a security processor. Now, the security processor can do multiple things. And by multiple things, it can do the intrusion prevention. It can do even AV scanning against that at the interface level. And it's simple to scale. You remember I mentioned the distributed system gets very complex as you start adding different I/O ports, and then you start trading off different processing. With the security processor, you get the ports and the processor at the same time. So the traffic coming in that port will typically be processed by resources that are on the card that forms the module. It doesn't have to be that way. Obviously, it can be configured in a number of different ways. But typically in this environment, there's a very defined set of traffic that needs to be processed by that security processor at the interface level and very quickly. So looking at a traditional firewall, so from the bottom, you see the I/O modules. These are the cards. These are the things that people think about. How many ports does it have? How fast are the ports? Can I get fiber ports? Are they copper ports? You know, how many, what speeds and feeds? That's a big decision. And then you have to process that traffic in some way. So in terms of firewall, there has to be a session created. You have to maybe apply the NAT, do whatever scanning, etc., examine the data, the payload, and so on. And then you have a management CPU that drives the user interface, maybe handles some of the logging and some of the general administration processes. So looking at one of our firewalls, so this is the bigger unit. Oops, there we go. So yes, we have physical ports as well. Be glad to hear. They have speeds and feeds. There's a thing we call the integrated switch fabric that maps the ports and allows you to program which resources can process which port information. But typically there's a one-to-one relationship across the module. So you come in on the ports and you use the processing on that module to actually handle that traffic. And then we have, depending on the configuration, you have the Forti ASIC, you have the network processor, or as I referred earlier, the security processor. So for low latency multicast, you're looking at needing the security processor. For high session rates and firewall throughputs, etc., you're looking at the network processor. So again, it depends on what problem you're solving as to what the system design needs to look like. And of course then you have the CPU to do the actual management functions just the same. And there's an additional ASIC set off to one side which does a lot of the kind of IPsec key generation and other issues around other solutions in the box. So What does that mean? It means you can get 2.5 microseconds latency, whether that's unicast or multicast, for a 64-byte packet. Now that is extremely quick. We have customers testing this, calling us up saying, are you sure it's actually doing something? It's like it's a wire. But I guess that's what wire speed means, right? Has to be as fast as a wire. That's not just in terms of throughput, but in terms of latency. Now, given that latency accumulates, given that you've got a millisecond here, there, and everywhere, reducing the latency in the firewall gives you that competitive advantage that you need in a finance environment. If you're just running email, do you care about 2.5 microseconds? Well, I guess for bragging rights you would care, but from a service perspective, no. But there are cases where you absolutely do care about the latency. So, as well as the latency, which I think I've banged on about quite a lot, what are the other requirements that we see? So, round trip time, 15 microseconds. So you can see at 2.5 microseconds, we're well in there. So we can get that sub 5 microsecond for both the unicast and multicast. 10 gig capability, true 10 gig. Now, what does true 10 gig mean? Well, as I mentioned, traditional firewalls can have problems with packet size because it's not just a throughput issue, it's a packet per second processing issue. So if you can't process the packets quickly enough, you can't achieve that true 10 gig speed. The other requirement we see is 2 gig of multicast. Now remember, the solution I showed was traditional firewalls having 100 meg. And we can have 4.5 gig. That's on one module, by the way. And you can have 5 modules. So in terms of multicast, the maths is pretty straightforward, but you get some very big numbers, certainly far in excess of the 2 gig requirement that we see. Small packet size. Constantly come back to this small packet size. Don't tell me what your performance is with 1,500 byte packets. It's not interesting. Okay? They very much want to know what the small packet size performance is. They also want some resilience in the solution. So having BGP and OSPF routing protocols running on the firewall itself is a requirement. With sub-second failover in an HA cluster, so when you're running 2 devices synchronized, having that failover to the alternate device in less than a second. But also there's a requirement, and this is a bit of a strange one, for virtualization. Now virtualization is kind of a misused word and gets thrown around in a lot of contexts these days. But for this, what I mean is that you can have 2 instances of the firewall running on the same hardware. Why would you want to do that in a finance environment? Well, what we see is that the market, the trading house, they're buying and selling services. There is a client network environment. So in this solution here, the kind of green and the yellow blob, they represent what we call virtual domains, but that's the virtualization, so virtual system, etc., various names for the same thing. But they represent the firewall instance on the box. So as you can see in this example, there needs to be a rapid and predictable failover of market data. Now, if you remember that market data is sent via multicast, you don't care how often you get that data, but you must get it. And engineering a solution like this means that you're getting the market data feed coming in from 2 different virtual domains, so 2 different firewalls, if you will, that are running on the same hardware. So the client is receiving that feed twice. They don't care that they're receiving it twice. they'll act on the information received. What they care is, should one of the components fail or be taken out of service, so let's remove one of those firewalls, that market data doesn't need to converge. You don't need to route back to the server because the market data has been sent to you twice anyway. So virtualization kind of didn't make any sense, certainly to me, in this environment, because you'd think you want to have everything quick, everything simple, everything fast. But in fact, when you start looking at resilience, you start to add a little bit of complexity. And when you're dealing with multicast, what you don't want to deal with is convergence times when things change. And in this solution, you don't need to do that. So, coming to the end. So, a financial market does have a fairly unique and very demanding set of requirements. And we haven't sat there in our ivory tower building a product in the hopes someone will buy it. You know, we've been dragged kicking and screaming to solve these difficult problems. And we have finance customers who insist that we solve these difficult problems. So we have, 9 of the top 10 banking companies as customers. Not all interested in low latency firewall. There are, if you like, traditional security solutions implemented as well. But when there is a low latency firewall solution, or when they're looking to re-engineer this market data activity and they're looking for the fastest possible environment, then they will come to us to see what kind of design will give them and meet their requirements that I kind of listed before. Okay? So there are some questions, if you want to. They're pretty straightforward, hopefully.
You mentioned you have this 4.5 gigabit you can put through the firewall.
Yeah.
And you mentioned also RDS, but RDS is very CPU.
Yes, yeah. So you're looking at 4.5 gig of firewalling. So with IDS, IPS, yeah, you're not looking at those same numbers. If you wanted to get that kind of throughput, then what you do is you take those security processes and you, what we call, cluster them together. So you're then looking at a more complex solution, but you have that processing.
And what is the factor of how is it turning slower with IDS?
If you have a fully populated solution, you can get to, it's about 12 gig, I would say, with IPS. But it depends how you measure IPS, right? It's one of these things, and 12 gig is an NSS number, if you like, an actual, as close to real life as you can get without just faking UDP packets, right? I mean, it's a proper traffic profile, etc., done with third party, so on and so on. So. All right? Right. Was anybody listening? So what is latency? Is it what you want it to be? Time for a coffee break. Is it your reaction to an event added to the delay in completing a task? Is it unavoidable but increasing? Is it the same as the link speed? Wow, look at that. I'm impressed, everybody. Yes, it's the longest one, actually. So I'm glad you didn't say time for a coffee break. Okay. So what is the impact of latency? Losing time means losing money? Nothing. We're dealing with small numbers here. No one cares. Round trip times increase, or data gets lost? Correct again. Time is money. Have I made these too easy? What's the final piece of any optimization strategy? Buy big servers, add more memory. Travel business class. Reduce the firewall latency. Put in higher bandwidth. Very good again. Okay, so one more. I'm not sure about throughput there, but anyway, what's the multicast data throughput Fortinet solution? Is it 100 meg, 2.5 gig? Fortinet is only able to provide unicast, or is it 4.5 gig? Correct again. Well done, everybody. Okay, that's 4 from 4. So any questions from the floor? I'm around the rest of the day, so if you do want to catch me, feel free.